Hello, students. Today we're going to go over the lab of Meg 10, viscosity, and this is part of the first year lab offered by the Department of Physics and Material Science, Chiang Mai University. So, theory. First of all, what I would like you guys to do is to flap your hand around, just like this picture. Just try to get a gush of wind into yourself. The thing is, what you would immediately realize is that the more you flap and the faster you flap, the more force that you're going to feel. So that force is from the fact that you're actually moving around in air, and air has a lot of air molecules such as nitrogen and other stuff. So when your hand hits the air, you would actually feel some air hitting you back. And this is the cause of the dragging force. So if you imagine riding a motorcycle at a very fast speed, then the faster you go, what you also realize is the faster you go, the more force you're going to feel. So this is what you call the dragging force. So here's a very simple experiment from Flynn Scientific. So if you drop like that little blue ball onto different water, different kind of liquid, so it would actually have different viscosity. So another thing that would actually affect the dragging force due to the viscosity is the type of materials that you're actually living in. So in this case, it's a different solution that would actually provide different drags. An equivalent of that would be if you try to run in water, the water would actually have more dragging force than the air. So if you compare the force that you feel as you move around, flapping your hand in the air versus in the water, you would actually feel different amount of force. So this is what we call the dragging force. We have established, according to Stokes' law, you know that when you drop the ball into this little flask right here, the test tube, you would actually have two forces. So one of them is mg, which is the force that's being dragged due to the force of gravity, and then you would have the buoyant force, which is the effect from the fact that some water is being displaced by the medium, by the material that's sitting in here. But then again, since this guy is actually moving inside of the materials, inside of the medium, it would actually have another force called the dragging force, and it's denoted by F eta here. So you would actually have the velocity that's going in one direction. So this velocity would actually make this ball hit molecules of the medium, and that the fact that the molecules of the medium are hitting this ball is causing this dragging force. So from Stokes' law, you would know that the dragging force is proportional to the velocity. So the faster you go, the more dragging you're going to feel. And also, naturally, the larger the ball that you're going to drop, Stokes has proven that when you drop a circular ball into the water, you would actually get a dragging force of 6 pi nu r v. And so basically, r is going to be the radius of this guy, and eta is going to be the dragging coefficient of the medium. So water would have a different eta than the soap water or whatever mixture they're using here. So you would have three different parameters that would affect the dragging force: the eta, the r, and the velocity. And eta is called the coefficient of viscosity, which is what we're going to be figuring out today in the lab that we're going to be working on. So, in theory, if you take a ball and drop it into a flask full of the whatever liquid you put in, so this liquid would actually have the coefficient of viscosity, and also it would have the buoyant force, and the mass would actually have mg. So as you drop it, the velocity of this ball is going to change, and then it would actually have different acceleration. So you want to consider the law of the Newton's law of motion. So since we know that we have three different forces, F eta, Fb, and mg, so F eta, you know from the theory that we learned earlier from Stokes, that it is 6 pi eta r vt, where vt is the terminal velocity. So which I will go over in a little bit. And there's a buoyant force, which is from the buoyant force theory. If you actually get displaced, if you displace the amount of water medium inside that replace water, the weight of that replaced water, which is equivalent to the volume of the sphere for that pi r cubed multiplied by rho multiplied by g, the weight of that displaced water is going to be equal to the buoyant force that's acting on here, and then you would actually be able to calculate the mg, which is basically the weight of this guy. So if you know the density of water and you know the density of the glass bead, you can actually calculate the mg as well. So once you know the three forces, you can actually act on it. But then again, we have the new concept here. V is not just any other V, but it's the terminal velocity. So terminal velocity is when you drop something into a dragging into medium with viscosity, then initially the velocity would change over time. But then again, once everything balances out, note that once everything balances out, you would reach what you call the terminal velocity. And this terminal velocity is like the reason why you would put a parachute onto the parachuter, so that like you would eventually drop at a constant speed. So at that constant speed, the people who are dropping would not feel any force because the force are at equilibrium. So here we would try to get the force, the sum of these three forces to be at equilibrium, so as to make it zero, so that the ball is going to be traveling with a constant speed of vt. Vt is going to be that constant speed, and acceleration would be zero once you reach the terminal velocity. So at terminal velocity, we have a equals 0. So from the Newton's law, you could actually equate all these forces. So Fb and F eta are pointing up, so you can put this guy on the left-hand side. And then the mg is pointing down, so you can put mg on the right-hand side. So from there, you could prove that eta equals this equation. But then again, since we're dropping the ball into like a very small flask, we would need a little bit of correction, which you don't need to know the derivation. But the final equation would look like this. So you can see that the eta, the constant of the constant of viscosity, can be calculated through this equation. And what you need to know is the radius of the cylinder you're dropping it on, the radius of the ball, the density of the liquid you're putting in row 1, and the density of the glass bead which you drop in row 2. And then what the other thing you need to know is the terminal velocity. So by getting all of these parameters, you could calculate eta. Okay, so what you're going to be doing here today is you're going to be measuring the little r, which is the radius of the ball, and the big R, which is the radius of the cylinder, and the Vt, which is the terminal velocity of the ball dropping down. So now we want to talk about the tools that we have. So first of all, we want to drop a ball into a glass bead into the flask or a cylinder. So what we're going to have is we're going to have a little bit of a plastic beads, which you will know the density of, and you will immediately drop it into a cylinder containing liquid, like illustrated in this figure. And then what you want to do is you want to observe how the bead is being dropped in here, and what's the motion looking like, and hopefully you would try to set up a starting point marked by this rubber band, so that like this starting point is going to be where you start calculating the terminal velocity. So you want to keep this rubber band, or the mark of the starting point, to be well below the surface, roughly 20 centimeters, to observe the terminal velocity. So hopefully after here, you would see terminal velocity. Okay? So, and then after it passed the starting point, you want to start timing it, and then let it run until it hits the finishing point, and then record the terminal velocity. So here is the actual setup that's going to be provided in the lab. And for those of you who are actually working on this as demonstration, you're going to be given 10 drops of the beads on top of the surface of the glycerine and the dishwasher. So these are viscous fluid which is contained in the glass tube. So what you want to do is you want to drop the little bead that are made of plastic onto the surface. So you can pick it up using a tweezer, and then put it close to the surface and then make a drop. So as you drop it, the ball or the bead is gonna slowly drop through the surface. So as you drop it, make sure you drop at the center and slightly on top of the surface. And then there are gonna be two marks, one on the top, another one on the bottom. So as it reach terminal velocity, you're gonna want to time the bead as it passed the first point, and then as you time it, you can use the information that you obtain by using the distance divided by the time it takes to travel from the top rubber band to the bottom rubber band during the terminal velocity time. And then again, you can just calculate Vt using S divided by T, and you just use the watch to measure T. Again, very important, you want to make sure that the first stop is actually like the point where the terminal velocity is already reached. So when you do the measurement, the bead is actually traveling at a constant speed, and you can assume the sigma force is 0, otherwise your assumption is going to be wrong. And also another thing is that you know that from the correction, you're going to need to know the size of the cylinder that is actually used as a container. So what you want to do is you're going to need to measure the size of the bead and the size of a container to get small r and the capital R. So the small r and the big R are going to be the parameters that you're going to be using to calculate the eta, which is the coefficient of the viscosity. So to measure the radius of the little bead, you want to use a micrometer. So open it up and then scooch over, stick the little bead in to measure the small r, and use that small r, do the measurement 10 or 20 times according to what your lab manual says, and that's how you get the average of the radius of the little r for the bead. And then you're going to need to know what is the big R given in the equation based on the lab notebook. So to get the big R, or the radius of the cylinder, so what you want to do is you want to use a vernier caliper multiple times on top of the cylinder, and then get a proper measurement. Again, use the bottom teeth to get the inner radius, just like what you did in Mech 1, and then scooch over and get a proper reading on the radius of these guys. So now here's how you measure the time. So first of all, as I mentioned earlier, you want to drop the bead on top and right at the center of the tube. So here I dropped the bead for you. As you can see, it's traveling with a non-constant velocity, but then again, at the first mark, you want to start the timer, because that mark is well below the surface, and after this point the terminal velocity can be assumed to have reached, and you want to measure the time it takes to travel from the top rubber band to the bottom rubber band. So start the clock and then keep a close watch. Once it reaches down there, stop the watch and read the time reading on the watch, and then you would know that the spacing, the distance, I think it's 20 centimeters. You want to check with the other video, but then again, once you know this, you can start working on the lab. Enjoy!